In the frozen darkness beyond Mars, something impossible is unfolding. Fresh measurements have captured 3I Atlas, a wanderer from distant stars, erupting with massive jets of water, launching nearly 40 kilograms every single second into the void. This isn't happening near the sun's warmth, but out where space runs cold and lifeless, further than Mars itself. The Swift telescope detected a flood of oxygen-hydrogen molecules, the unmistakable signature of liquid activity in a region that should be silent as death. Not even Oumuamua or Borisov, our previous interstellar guests, shattered the rules this dramatically. Everything we thought we understood about comets is crumbling. Either our fundamental theories are catastrophically wrong, or Atlas is demonstrating chemistry that's never been witnessed in our entire solar system. The question burning through the astronomical community: why does this interstellar object appear so eerily alive in the cosmic deep? What critical piece are we still missing? 40 kilograms per second. That's not an estimate. That's the confirmed water loss from 3I Atlas, measured while stranded 3.51 astronomical units from our star, where sunlight barely whispers across frozen surfaces. Most comets can't generate water vapor this far out. Yet the Swift ultraviolet optical telescope, orbiting high above Earth's atmosphere, captured the undeniable ultraviolet signature, counting hydroxyl radicals at 1.35 times 10 to the 27th power molecules escaping every second. Each one represents a water molecule ripped apart by distant starlight. This isn't instrument error or wishful thinking. Scientists stacked over 2 hours of ultraviolet exposures with 40 minutes of visible light imaging, filtering signal from cosmic background noise. The conclusion is absolute. This interstellar comet is venting water at rates matching objects much closer to solar warmth, completely rewriting physics textbooks on what's possible in the deep freeze. Standard comet behavior dictates waiting until approximately 2 astronomical units from the sun before water ice begins serious sublimation. Atlas demolishes those expectations. The measurements demand at least 8% of its surface must be actively venting to sustain this impossible outflow, nearly double the 3 to 5% typical for homegrown solar system comets. The coma surrounding it isn't some wispy veil, but a thick, churning envelope of gas and dust. Through careful image stacking and mathematical subtraction, researchers mapped the geometry of this cloud and discovered something stranger still. Water isn't simply boiling off the main body. Instead, it's streaming from countless icy grains, microscopic debris ejected from the nucleus, each fragment acting as a miniature steam engine drifting through the coma, flashing to vapor under faint sunlight. This extended source model changes everything. Rather than a sealed crust trapping ancient ices beneath, Atlas surrounds itself with a halo of sunlit particles, each one contributing to the torrential release. Laboratory experiments confirm this possibility. Micron-sized water ice grains exposed to solar radiation can sublimate efficiently even at these extreme distances. The process operates subtly, but the data doesn't lie. The comet's activity curve, reconstructed from historical observations and ultraviolet spectroscopy, climbs where every model predicted flatline silence. Some researchers propose photodesorption, where ultraviolet photons physically kick water molecules free from ice surfaces. Others point toward crystallization of amorphous ice, which releases trapped gases in sudden exothermic eruptions. But at these temperatures and distances, no single mechanism perfectly explains what we're witnessing. The sheer magnitude of water loss, measured with cutting-edge instruments and confirmed across multiple wavelengths, creates an unforgiving constraint that any theory must satisfy. Right now, 3I Atlas stands as a direct challenge to comet science, an interstellar visitor breathing in darkness, carrying secrets in every escaping water molecule. 3 interstellar visitors, 3 radically different stories. First came 1I Oumuamua in 2017, sweeping through as a silent, tumbling fragment. Bone dry, no surrounding cloud, no tail, not a single detected molecule of water or carbon monoxide. Astronomers watched in mounting frustration as it vanished into darkness, leaving only its bizarre shape and mysterious acceleration, never revealing the chemistry of an active comet. 2 years later, 2I Borisov arrived, looking and behaving like a classic icy wanderer, shedding water and dust in sunlight. Its cloud and tail matched familiar blueprints of solar system comets, complete with that characteristic faint blue-green glow of cyanogen. Borisov brought comfort, proving at least some interstellar objects follow known rules. Then 3I Atlas appeared, and the rulebook exploded. Instead of a slow, predictable brightness increase approaching the sun, Atlas's light curve rocketed upward like a solar flare. Photometric data revealed a superlinear surge, not gentle warming, but sudden ignition. Brightness didn't just increase, it detonated, exceeding predictions for an object at that distance by staggering margins. This wasn't gradual surface ice thawing. Something deeper, more volatile was awakening beneath the crust. The color shift told its own dramatic story. As Atlas brightened, its surrounding cloud transformed from typical dusty white to an eerie, luminous green. That glow marks cyanogen radicals, CN molecules lit up by starlight, the classic fingerprint of active chemistry. But there's more. Atomic nickel lines, rare and completely unexpected, flickered through the spectrum, adding a metallic signature to the comet's palette. Unlike Borisov, where cyanogen appeared early and faded gradually, Atlas held back, then unleashed its green emission in a sharp chemical explosion, as if a hidden switch triggered deep inside the nucleus. This behavior breaks the pattern set by previous interstellar and even solar system comets. The activity curve doesn't climb, it leaps. The onset of green emission combined with exotic metals suggests a layered interior, with volatile ices and trapped gases stacked beneath inert material. As sunlight penetrates deeper, thermal fractures and sudden phase changes release these hidden reservoirs in unpredictable bursts. The surrounding cloud becomes not just debris, but a laboratory. With icy grains, radical molecules, and metal atoms swirling in luminous chaos, each one a clue to the comet's alien birthplace. Atlas represents a completely new archetype, not dry and silent like Oumuamua, not comfortably familiar like Borisov, but hyperactive, chemically restless, and visually electric. Its superlinear brightening and delayed green glow demolish every model of comet behavior. The burning question now: what chemistry drives this explosive switch, and what secrets hide locked inside the layers of an object born beyond our sun? Nickel without iron. That phrase has been echoing through comet science channels since July, when the Very Large Telescope captured 3I Atlas's cloud lit up with atomic nickel lines while iron remained completely hidden. Spectra captured in the 3D400 to 3600 angstrom window recorded as the comet drifted approximately 2.8 astronomical units from the sun, show a metallic fingerprint that shouldn't exist. In every solar system comet studied so far, iron and nickel travel together, typically in a 10-to-1 ratio. On Atlas, nickel stands alone. Dr. Veronika Kubler, lead spectroscopist on the VLT campaign, became ground zero for this anomaly. Her calibration procedures, line identifications, even her reference star choices faced intense scrutiny. Yet each new exposure set confirmed the pattern. Strong, isolated nickel emission, iron lines barely registering above background noise. The numbers forced a reckoning across the field. Some modelers argue for fractionation during formation. Perhaps Atlas's parent disk separated nickel and iron, leaving one at the surface while the other remained buried deep. Others point to exotic chemistry. In a carbon monoxide-rich environment, nickel can form volatile carbonyls, compounds that shatter under sunlight, releasing nickel atoms into the gas phase. Iron carbonyls, by contrast, are far more stable and difficult to create or destroy. A third faction blames space weathering. Cosmic rays and micrometeoroid bombardment could have sculpted a weathered surface layer, stripping away iron or locking it in resistant minerals while nickel accumulated in more fragile phases. Still others look toward the comet's birth environment. If Atlas formed around a peculiar disk with unusual metal ratios, the answer might be encoded in its core composition. no single mechanism fits all observations. Each hypothesis demands different connections between nickel, carbon compounds, and the comet's volatile inventory. For now, those nickel lines hang in the spectrum like an unanswered challenge, proof that Atlas's chemistry is stranger and more revealing than any comet humanity has encountered. Carbon dioxide dominates the cargo manifest of 3I Atlas, near-infrared spectra from the James Webb Space Telescope and ground-based observatories revealed something almost unprecedented: carbon dioxide abundance outpacing water vapor, possibly making carbon dioxide the dominant volatile in the cloud. For comet chemists, this is a massive red flag. In our solar system, water almost always dominates. Carbon dioxide rarely takes the lead. Here, the ratios flip completely. Dr. Anaïs Marron, a comet chemistry specialist, explains that such extreme carbon dioxide to water ratios mean Atlas likely formed in an environment far colder than the birthplace of most known comets. Only in the deep freeze of an outer protoplanetary disk or under a dim, low ultraviolet star could so much carbon dioxide survive locked in ice. The timeline of chemical release adds another mystery. Cyanogen, responsible for the comet's green glow, appears late, weeks after initial outgassing began. In Borisov, cyanogen showed up early, rising with the first activity signs. Atlas holds back, then releases a sharp burst as if a chemical trapdoor opened deep within. This delay suggests layered ices or exotic trapping mechanisms, with cyanogen locked beneath more volatile compounds, only freed when the comet's crust fractures or grains get ejected into sunlight. Spectra indicate much of the gas isn't streaming straight from the nucleus. Instead, icy grains drift through the cloud, each one a tiny capsule of primordial material, releasing carbon dioxide and water as they warm. The bizarre volatile mix, carbon dioxide-rich, water-poor, with delayed cyanogen flare, paints a picture of a comet formed far from any sun's warmth in an ancient frozen disk. Some have speculated about ingredients for life, but experts urge caution. Chemistry, this exotic represents a fossil record, not a biological seed. The story written in Atlas's cargo is about birthplace, not biology. Nickel atoms forged in dying stars carry supernova memories across the Milky Way. In 3I Atlas, the presence of nickel isolated without its usual iron partner offers more than chemical oddity. It's a fingerprint from another galactic neighborhood, a clue to the processes that shaped both the comet and its parent system. Galactic. Thick disk stars, older and metal-poor compared to our Sun, sometimes display subtle shifts in their nickel-to-iron ratios. But the gap between those stellar trends and the extreme nickel dominance in Atlas is enormous. The comet's spectrum is a message in a bottle, hinting at local chemical quirks layered atop galactic history. To fully decode that message, astronomers need more than elemental lists. They need isotopes. Nickel-60, for example, forms when massive stars explode, while nickel-58 traces quieter stellar lifetimes. Measuring ratios between these isotopes would pinpoint whether Atlas's nickel comes from ancient supernova debris or longer-lived, quieter stars. But this isn't possible with today's telescopes. Only the next generation, giants like the extremely large telescope with enough light-gathering power to resolve faint isotopic lines, will separate these cosmic signatures. Until then, the nickel anomaly stands as both puzzle and promise, a falsifiable test awaiting better data. Some community members have floated ideas that such a sharp nickel signal could be artificial, a technosignature, evidence of engineered material. Most researchers push back hard, pointing to natural, if exotic, chemistry. The standard remains clear. Extraordinary claims demand extraordinary testable evidence. For now, 3 Atlas's nickel acts as a galactic messenger, inviting humanity to map the chemical diversity of worlds beyond our own. The odd radio circle detection pipeline has become a model for anomaly hunting, blending computational power with human pattern recognition. This same approach now shapes how astronomers search for the unexpected in data from objects like 3I Atlas, where every outlier could rewrite fundamental rules. Pattern seeking is hardwired into human brains, and nowhere is that more obvious than when a comet shares the sky with familiar planets. In August 2025, Mercury and a series of other planets both reached their visual peaks just as 3I Atlas passed through the inner solar system. A TikTok video claiming cosmic alignment between these objects racked up nearly 500,000 views in 4 days, spawning hashtags and copycat posts across Twitter and Facebook. Graphics mashed together their orbital tracks, hinting at hidden meanings and cosmic energies. The reality: Mercury's elongation and planetary opposition were routine events. Their alignment with Atlas was coincidence of perspective, not physics. Astronomers quickly debunked the claims, but correction posts barely reached a fraction of the original audience. This is the engine of viral myth-making: a striking image, a suggestive phrase, and a gap in public understanding. The lesson is simple. Transparent, timely communication is the best defense against viral myths. Otherwise, coincidence and information gaps become raw materials for the next sensational story. The next phase in comet science is already under construction. The Verum, Rubin Observatory, set to begin full operations in late 2025, will scan the entire southern sky every few nights, catching interstellar visitors like 3I Atlas before they vanish. The square-kilometer array, coming online shortly after, will amplify the search for radio anomalies and odd radio circles, blending citizen discoveries with algorithmic sweeps. Together, these surveys promise not just more objects, but richer, faster data, chemical fingerprints, dust-to-gas ratios, and first real-time alerts for rapid response. Astronomers are drafting ambitious wish lists. High on the agenda: tracking the emergence of iron lines in Atlas's spectrum as it swings closer to the Sun, mapping dust color shifts, and measuring